Good morning. So let us continue our lesson. So do you remember we were actually completing a table of derivatives. So let me write what we have so far here. So we have the function f and its derivative here. So we learned that the derivative of a constant function is 0. We learned that the derivative of x to the power c is cx to the power c minus 1. And then we also learned that the derivative of sine x last time is cosine x. And the derivative of cosine x, of course in radian mode, is minus sine x. We also discussed what will happen if x is measured in degrees, but I told you that mainly we will use this degrees. So we want to add some more functions here today, and one of them is e to the power of x. E is the Euler number, which is a very famous number in mathematics, and you are familiar with it from your Math 3C studies. And then we have a to the power x. Yes. And then we want to talk about logarithmic functions, natural logarithm ln of x, and we can also talk about a little bit of log of x in some base 8. So we want to try to answer these question marks today. Yes. I will try to find my videos in Math 3C related to e to power x and things like that. If you have forgotten something and you want to understand things very deeper, you can refer to those videos, but I will write the results that we need here. Okay, so the first function that we want to talk about is the exponential function whose base is the Euler number. So Euler number is also a very famous number in mathematics, like the pi number. So E is some number around 2.72 if you want to round it up to 2 decimal points. So let me write approximately this number. And it turns out that E is an irrational number. So these decimal places will go forever. But exactly like pi, that we usually use letter pi to denote the exact value, we use letter E for the Euler, the mathematician, to denote this number. And we usually don't work with its number unless we want to do some practical work and calculation. So today we want to see what happens if I have this function and I want to find its derivative. Of course, this is a Math 3C lesson, but let me remind you as much as we can. And this is a very, very nice function because it turns out that the derivative of this function is equal to itself. Yes? So if I want to calculate the derivative from scratch, there is only one way for me to do that, and that is the definition of the derivative. Yes? So this becomes the limit of f of x plus h minus f of x over h. H goes to 0. And what I have to do, I can write the limit h goes to 0 minus sine f of x is e to the power x, and f of x plus h means that I have to replace x with x plus h everywhere. So this becomes e to the power of x plus h, yes? And then of course I can write it in this form. I can write it as e to the power x multiplied by e to the power h minus e to the power x divided by h. H goes to 0. And then I can factor e to the power x out, and let me write it here. So e to the power x multiplied by e to the power h minus 1 over h. H goes to 0. Okay, the point is that I have to calculate this limit, but this limit is also one of those limits that you need to know a little bit more advanced mathematics to be able to prove it rigorously. But you can convince yourself by calculating some numbers, yes? So for example, you can use your calculator, e to the power h minus 1 divided by h, and then you have h. For example, you can choose numbers like 0.1, 0.01, 0.001 and calculate this expression. You will get some number here, some number here, some number here, and you see that if I send these numbers closer and closer to 0, these numbers are getting closer and closer to 1. But of course, this is not a rigorous way of proving this. These kinds of limits you will definitely study. Of course, I haven't checked that book, but I think they have done it rigorously under the title of for interested students or something like that. Yes. So if you want, you can also check it in the previous chapter. But we don't have time for it. If you want, you can study, and if you have questions, we can talk about that together. But anyway, this limit becomes 1, and this becomes e to power x. So now I can just clean that question mark and write e to power x here. So this is a very simple function whose derivative is equal to itself. And of course, in Math 3C, might be you are familiar with this one. So do you remember in Math 3C we had the formula for the derivative of this function? This is c e to power cx. Yes? But I don't need to express this one because that is the chain rule actually. At that level, we couldn't talk about the chain rule, but that is exactly the chain rule. Why? Because if I ask you what is the derivative of e to power u, what is the answer? Do you remember? If u is x, the derivative is in the table, that will be given to you. But if the exponent is a function of x, not just x, I use the same rule, so it becomes e to power u, but because of the chain rule, I have to remember to multiply by u prime. Yes? So whenever we have a new formula there, you can also read the chain rule version of that formula. And this is why I don't want to write that. Of course, you can use it, but this is what you learned in Math 3C. Now you can understand it using the chain rule, yes? Why is that? Because here I take this u in my head, then e to power u prime becomes e to the power of u, which is cx, multiplied by u prime. Yes? But what is the derivative of cx? Is just c. So this is the reason that you see here. You see c here, yes? So yeah, that's up to you. If you want, you can memorize it in that way. Okay, so derivative of this one. If I want to give you some examples, I can write, for example, if I give you a function like this, e to the power of square root of x squared plus 1. And I ask you what is the derivative of this one. Okay, how should I do that? I will take this one, u in my head, yes? How many functions are involved here? I have x squared plus 1 function first, and then a square root function comes in, and then exponential function. So this simple function is a combination of 3 functions actually. So what should I do? I need to take the whole thing here to be u, and then I will have e to the power of u. Taking x squared plus 1 to be u at this stage is not useful, because if I take this one to be u, then I will have e to the power of a square root of u, which is not in my table. Yes. So these are more or less the same thing. I will not be able to repeat all of them again, but this is the idea. So I will take this one to be u. That's a good choice, because then I will have e to power u, and I just know what to do. So I take the derivative, it becomes e to power u, but multiplied by u prime. Yes? And now this time, I will take this one to be u, and then e to the power of a square root of x squared plus 1. The derivative of a square root of x, we know, is 1 over 2 square root of x. So this becomes 1 over 2 square root of u, but multiplied by u prime. But this is very simple. The derivative of u prime is simply 2x. So this expression that you see here is the derivative of this function. Now, is that clear? Okay, so now we want to go to the next one, in which here a is positive and not equal to 1. This is usually written in that way. That's also good, but I would prefer to write c to power x to make it clear for you what is the difference between this one and that one. So here you see x is variable, the exponent is constant. Here this is the other way around. The base is constant, the exponent is the variable. So please appreciate the difference between these two. They are different rules. Yes, this is called a power function. This is called an exponential function. So they are different. Yes, so the rules are also different. So if I want, by the way, if a is 1, the reason that 1 is excluded is because 1 to power x is 1. That's a constant function. And the reason that I have to consider a positive, because if I don't consider a to be positive, then I will have problems with some of these x's. For example, if I take x equals to -1, and if x is 2, I don't have any problems. But if I take a -1 and x 1/2, this becomes the square root of -1, which would be problematic. So when you talk about an exponential function, you're always talking about a function like this in which the base is positive and not equal to 1. So under these circumstances and under these conditions, I want to find the derivative of this function. So how should I do that? One way, of course, is to write it in this way, which gives rise to a limit that you again don't know. Okay. So for example, if I start from scratch and I ask you what is the derivative, one way is to write the formula for the derivative from scratch. Then this becomes a to power x plus h minus a to power x divided by h goes to 0. And then I have to, if I want to do the same thing, I can factor a to power x out. This becomes a to power h minus 1 divided by h goes to 0. Then it means that I have to consider the limit of that part. But discovering the limit of that part using this trick is not easy. And you will see why. I can tell you later what is that limit. But if you want to use the same process, it is not that easy to guess what the value of that limit is. Okay, you can see that the numbers are getting closer and closer to something. But that guessing that what that number is not that easy. Yes? You will see why in a minute. So, is there any other way that I can do that? You need to know a little bit about logarithmic functions. I don't know how much do you remember. Let me just review a little bit. So, you know that this is the function f of x equals to ln of x. It's called the natural logarithm of x. This is meaningful if x is positive. Otherwise, it is not defined. And what is the meaning? Do you remember anything about ln? So what is logarithm? Do you know? If you have a function f of x, so let me change it. If I have a function log of b in base a. First of all, for this makes sense, b should be positive, a should be positive, a shouldn't be equal to 1. And when you say that the log of b in the base a is equal to, say, for example, c, what is the meaning of this? This means that a to power c is equal to b. This is the meaning of the logarithm, yes? So for example, if I ask you what is log of 16 in base 2, what's the answer? The answer is 4. Why? Because 2 to the power of 4 is 16. Okay? And now, so for having a base, this number should be positive and not equal to 1. If I choose this base to be the Euler number, this number, if I choose the base to be the Euler number, instead of writing log of base in base e, people simply write it as ln of b, ignoring writing those things. And of course, you might remember that if a is 10, we also have another convention. If a is 10, instead of writing log of b in the base 10, we simply ignore writing t
and write log of b. So if you see log of b without this number in the base, it means the base is 10. And if you see that it is written ln of b, it means it is a logarithm whose base is the Euler number. Yeah, so these are the things that you should remember from Math 3C. Okay. Okay, there is a very important formula that is relevant for us. By the way, so this means that this natural logarithm is indeed a logarithm. So whatever a logarithm you have, a formula, whatever formula you have for the logarithm, you also have it for ln. For example, I don't know, if I ask you what can I write for ln a to power x, you know that this x can go behind the log, yes? And you can write it like this. Yes, I don't know, if you have a ln of a plus ln of b, you can write it ln of a times b. If I ask you what is ln of a minus ln of b, the answer becomes ln of a divided by b. So these rules, hopefully you remember. And if you don't, you can ask me questions. But one rule that is very important for us is actually more or less the definition of the logarithm, yes? So let me explain it here. So when I told you that log of b in base a is c, this means that if I raise a to power c, the answer becomes b. That's the meaning, yes? And now take c away and put its equal number. So what happens then? Then it becomes a to power log of b in base a is b. So that's actually the definition of the logarithm. If you have a and you raise it to a log of a number whose base is exactly this number, then this becomes b itself. Of course, if b is positive and if a is positive and not equal to 1. Yes? Now, let me write this formula by changing a to the Euler number. Then what will happen here? It becomes e to the power of logarithm of b in base e is equal to b. Yes? And now people, I told you that instead of writing log of b in the base e, people write ln of b. So this means e to the power of ln of b is equal to b. So that's a very important formula. Yes? By the way, so let me ask you this question. What is ln of 1? What is ln of e? These numbers you need to know. These are exact. What is ln of 1? ln of 1 is 0, yes? Because the base is e. E to power 0 is 1. That's correct. What is ln of e? It's 1 because e to power 1 is 1. So these numbers are exact. So this is the formula that I want somehow to use instead of this method. Okay, so how do you think I can use it? So let me write the question again. The question is that f of x is a to power x. And I told you that a is positive and not equal to 1. I want to find its derivative. So how can I do that? Let me write here. So f of x is equal to a to the power of x. A is positive, a is not equal to 1. Yes? And then the question is that what is its derivative? And I told you there that if e to the power of ln b becomes equal to b if, of course, b is positive. So this is the formula that we will need somehow to find the derivative here. Because I told you that if you want to start it from scratch, you have to know how to calculate this limit. And this process, which was manageable for e, will not be that manageable for any arbitrary number. You will see in a minute why. It is not easy to guess what that number is. of course, you can have some guess. Why this is hard to guess? Do you think? Because here a can be any number that you like, positive and not equal to 1. Of course, if I change a, this limit will start changing. So it means that the value that you will get for this limit is not a constant number. In the previous case, this was 1. But in this case, it depends to the choice of a. So it means that if you change a from one number to another number, this limit will change. So then you need to find a pattern so that I will be able to guess for any number a, not just for one a. And guessing it for any number a might be not that easy. Okay, now the question is that how can I calculate the derivative of this function using this idea, using this formula? Any ideas? So you see, this formula tells you that if you give me a positive number, very simple, innocent positive number, I can write it more complicated. Yes? But usually people want to write things simpler, but sometimes making things harder in the long run will be better. So now, do you know what to do? So I want you to make this a little bit complicated using this formula in a way that you can use the previous result to calculate this. Yes?
Okay, so before you take the derivative, you write a as e to the power of ln of
Exactly.
a.
So here you see, this is one of those few steps that few moments that we make things harder. So instead of a, I can write e to the power of ln of a. But of course I have an exponent x, so I have to write it in this form. Yes? But then this is an exponent exponentiated once more, so I have to multiply the exponents. So this becomes e to the power of ln of a multiplied by x. So now, do you remember I told you that if e in the previous lesson, if I take you this, if I ask you what is the derivative of this, we prove that this becomes this. So now give the role of c to this number. This is a constant number. A is a constant number, ln of a constant is a constant number, so that can play the role of my constant here. And now I am asking you what is the derivative of that. According to the rule that I discovered, the constant should go down. So the constant is what? ln of a, yes? And then I should repeat the same function. You see, c goes down, the function is repeated. So this means that ln of a, which is playing the role of the constant, goes down, and the function should be repeated. Yes? That's it. So that's the derivative. But I can rewrite it back into the simple form now. So I made it a little bit more complicated, use that result, then I don't need to write it more complicated. I can switch back to the original form. This is exactly f of x, so it's a to the power of x. So this becomes ln of a times a to the power of x. Yes, so that is the formula that we need. So if I have an exponential function, the derivative of exponential function is the function itself multiplied by ln of a. By the way, the same holds for e, yes? If I have e to power x, this becomes e to power x but multiplied by ln of e. But ln of e is 1, so that is why you get this one. So this is why it was a little bit complicated. Now, hopefully you realize, now can you answer that limit? What is the value for that limit? Because the derivative, we calculated using that. So it means that now we know the answer to this limit. Not by calculating the limit, by calculating the derivative in a different way. Because I am calculating derivative in two different ways, these two should match. So it means that this answer to this should be a to the power of x multiplied by ln of a. Yes? So then what is the limit which was missing? What is the limit now? You see, this should be a number so that when you take the limit and multiply it by a to power x, gives you a to power x multiplied by ln of a. Hopefully it is clear the limit of this part is ln of a. Yes? So that is an indirect way of calculating the limit. And this is really clear that why it was not easy to guess, because, so let me write this here for you. So we realize that's an important limit. The limit of a to power h minus 1 divided by h goes to 0. If a is positive and not equal to 1, under these conditions, this limit is ln of a. And for example, if I tell you what is this limit, the answer is ln of 2. ln of 2 is not a number that you can guess by seeing the pattern, yes? ln of 2, if you calculate it, it's a not very familiar number to us. And by the way, even if you can guess it is ln of 2, for 3 it should be ln of 3, for 4 it should be ln of 4. So that is why we couldn't guess if you follow that strategy. But this formula turns out to be true for a equals to 1. Why is that? Because if a is equal to 1, 1 to power h is 1, 1 minus 1 is 0, the limit is 0. On the other hand, if a is equal to 1, ln of 1 is also 0. So if I exclude this and just write a positive, that is not wrong. But we can keep it like that. So okay, so I will add this here. So I can clean this question mark now. Then I would write this becomes the same function, but it is not finished. I have to multiply by the ln of the base. Yes? And then if I ask you what is the chain rule version of that, the chain rule version of this derivative, it becomes the same function multiplied by ln of a. This is the normal way of derivative if u is x, but because of the chain rule, I have to multiply by an extra u prime always. Yes? So let me write one question. So if I give you this, I want to write both of them in one question. So x to power 3 plus 3 to power x. If I ask you to differentiate this function, be careful. One of them is the second formula that we have on the board, which is this formula. The second one is this formula we discovered today. Yes? So be careful and differentiate between these two functions. So the derivative of this is not an exponential function. It's a power function because x is variable, the exponent is constant. This one is an exponential function. The base is constant, the power is variable. And then this one, the derivative is 3x squared. But this one, be careful, don't write x, 3, x to the power of minus 1. No, you have to change the rule. It becomes 3 to the x, ln of 3. Yes? Okay. Let me just finish this and then we can solve some more examples together. I think these are very simple. Okay, now what is your idea about calculating the second, this question mark, ln of x? How should I calculate the derivative of ln of x? One answer is to start from scratch again, but unfortunately it will give, of course, that limit in Math 3C. When I was teaching, I actually taught how to calculate. But let us forget about that for the time being and try to calculate the derivative of ln of x using a very nice trick. So let me write. If I ask you what is the derivative of this one, so if you want to calculate the derivative from scratch, you have to write f of x plus h becomes ln of x plus h minus ln of x divided by h goes to 0. If you remember what I told you in Math 3C, I will try to find those videos and put the links for you, even below this video on YouTube. You should be able to calculate this limit somehow. But it turns out to be hard. Today, because we know the chain rule, we can do it faster. Okay, how do you think I should do that? So the question is this. Y is equal to ln of x. What is y prime? I intentionally write it in with y to tell you how you can do that in principle. How should I do y prime? One way is this, but forget about that one. Let us go back to a different way. What is x? Can you tell me what is x? If y is equal to ln of x, what is x? Yes?
E to power y.
E to the power y. So from here, you can get this that e to x is e to power y, yes? Okay, now you can view this as equality of two functions. One function, for example, g of x equals to x, and one function is this one, but of course you don't see x, but you know that y is a function of x. Yes? So if this function is equal to that function, the derivative of the function on the left should also be equal to the derivative of the function on the right. Yes? But now if I ask you what is the derivative of x, the answer is simple. It becomes 1. I want you to tell me what is the derivative of e to power y. Y is not a constant, is not x, be careful. Y is a function of x. Yes, do you agree? So what can I write? What is the rule for the derivative of this function? It becomes the same function, but multiplied by what? Multiplied by? Yes? No. ln of e is 1. No, the chain rule. This y, what is the, so if I ask you what is the derivative of e to power u, what is the derivative of e to power u? The derivative of e to power x is e to power x. What is the derivative of e to power u if u is not x but a function of x? What is the answer? E to the power of?
E to power u multiplied
By u prime. This is u actually, because y is not x, is a function of x. You see it. Y is not equal to x. Y is a function of x. So you have to use the chain rule. It becomes e to power u, which is e to power y in this case, but multiplied by y prime. But I am looking for y prime. So y prime is found here now. Yes, y prime is equal to 1 over e to the power of y. But that is not a good formula. Why? Because I have given you y as a function of x. You expect a formula which expresses y prime in terms of x, not in terms of y. But that is easy because e to power y is x. Yes? And then it becomes 1 over x, as simple as that. So the derivative of ln of x is 1 over x. Is that clear? So this is much better than calculating this limit. So let me write this here. This question mark now I clean. This becomes 1 over x. But this formula is true if x is positive. Because otherwise ln of x is not defined in the first place. Yes? For example, now can you tell me what is ln of u prime? So ln of x prime is 1 over x. What is ln of u prime? Is 1 over u, but not finished. You have to multiply by u prime. And usually people write it in this form. So that is a good combination to remember. If you have a fraction whose numerator is the derivative of its denominator, you need to remember that this is the rule for the derivative of ln of u. So let me write it separately. That's a good combination to remember. I don't know, for example, can you tell me what is the derivative of this function? ln and logarithms are like sine and cosine. When you have 3 here, it means the whole expression to power 3. So when you write ln of 3 to power x, it means ln of x totally to the power of 3. It's exactly like sine function. Do you remember sine to the power of 3x means sine of x to power 3? For logarithms, we also put the powers here. So if you want to differentiate this function, how should I do that? I have to use the chain rule. But which one plays there? How many functions are involved? Again, x2 plus 1, one function, and then this natural logarithm, and then raising to power 3. So there are 3 functions involved again. So if I want to differentiate it, you remember I told you that take this one to be u. Why is that? Because then you have u to power 3 and you know what to do. So the derivative becomes 3u squared multiplied by u prime. Yes? And then today we'll learn what is the derivative of ln of u. Now I will take this one to be u, so I continue. This becomes 3 ln squared x squared plus 1. The derivative of this one becomes 1 over x squared plus 1, but multiplied by the derivative of u. And finally, this becomes 3 ln to the power of 2 x squared plus 1. You can write it as, you can make it in the denominator x squared plus 1 and then multiply it by 2x. So that is your derivative. Yes? But let me also write another formula here. If I ask you, so the bad point about this formula is that this is only valid if x is positive. Otherwise, ln is not defined. So we learned that the derivative of this function is simply 1 over x. But this is a better formula if I put absolute value here. Yes? This formula, this ln of x, has a lot of limitations. I cannot put 0 there. I cannot put any negative numbers there. But if I put absolute value around that, then I have only one limitation, and that is x equals to 0. X cannot be equal to 0. But here I don't have any problems with negative numbers. Because if I put negative numbers here, absolute value makes them positive, and then you have ln of a positive number, which is good. The nice thing is that the derivative of this one also turns out to be the same. Okay, so I saw that this is in your book. That is good that they have discussed about that. So let me also calculate this. Now assume that you want to calculate the derivative of this. What is your suggestion? So question is that, what is the derivative of this? It's a little bit tricky because we don't know the derivative of absolute value. So what is your suggestion? Can you write absolute value in a way that doesn't involve absolute value? It involves the square roots. Yes? How can I write that? So I can write y is equal to ln of, ln of what? Absolute square root of x squared. Do you remember a square root of x squared is not x, it's always absolute value of x. Okay, and then we can continue. How, for example, this one, I can write it as ln of x to the power of 2 to the power of 1/2. Yes? And then I can bring 1/2 back. Then I will have ln of x squared. By the way, can I bring these 2 back as well? These are important things that you need to be careful. So can I say that? So we know this formula. You have seen that. I am not saying this is wrong. Have you seen this formula? That we can put p back. Yes. This is one of the famous properties of Ln. Probably you have used them a lot. But this is, you have to be very careful, because do you think that this is always true? Using this formula, I am putting these two back. Do you think this is always true? Yes?
Not for negative values.
Not for negative values. And it's extremely important to be careful, because if I write Ln of minus 2 to power 2, do you think it is meaningful or meaningless if I ask you, is this defined or undefined? This is definitely defined, because minus 2 to the power of 2 is positive 4, and having positive 4 in front of Ln doesn't have any problems. But if you carelessly follow this rule blindly without considering the conditions for that formula, if you take this away here, this becomes 2 times Ln of minus 2. If you use your calculator to calculate this, you will get an error message because it is not defined. This is defined, this is not defined. You cannot say that they are equal. This is meaningless. So whenever you want to use formulas, you have to know when they are applicable. Okay, so here this formula works if A is positive. Otherwise, this is meaningless. Yes? If P is even, this makes sense if A is also positive. So this means that this is the reason. I don't have any problems with moving 1 over 2 back to the back, but I will have problems if I want to move 2 to the back as well. Yes? Because of that reason. Because here, can x be negative? The answer is yes. But so here, still x can be negative. But if I move this one to the back, x cannot be negative. So this means that these two are different. I have to stop there. I cannot move 2 to the other side. If x is positive, yes, I can move it. But I don't have guarantee that x is positive. It might be x is negative, yes? Okay, so I have to start the differentiation right here. So the derivative of this one, that is a constant, so I don't care about that. And we just learned what to do with the derivative of a function. The function goes down, and I have to differentiate it in the numerator. And then you see that this 2 and that 2 are cancelled. X over x squared is cancelled. I will get the same answer back. So it doesn't matter if I calculate the derivative of ln of x, it becomes 1 over x. If I calculate the derivative of ln of absolute value of x, it becomes 1 over x. But the domain of this is larger. Yes, here, if I want to calculate this, x has to be positive. Okay, but if I want to calculate the derivative of this one, x could be negative, but it cannot be equal to 0. Then the derivative is again 1 over x. So that I saw also in your book somewhere, so it's good to know about it. So the derivative of ln of x is 1 over x. The derivative of ln of absolute value of x is also 1 over x. But this is valid if x is positive. This is valid if x is not equal to 0. This is valid even if x is negative. This is only valid if x is positive. Okay, and I want to answer the last question, Mark. Do you know how to answer that one? So here, this is an exponential function, a particular form, whose base is the Euler number. The general formula is this. This one is also a particular logarithmic function, a logarithmic function whose base is equal to e. But what happens if the base is not e, an arbitrary number a? Okay, so that is the question that we want to answer now. Okay, I don't know how many of you might be able to answer that, but we had it in Matematik. I don't know the people who had it with Aladdin, have they talked about this or not, but it was not part of the lesson, so I knew that would be necessary, so I told the students to know about it. Oh, okay, not Math 3C, Math 2C, yes. We did it in Math 2C. So I don't know why this formula is missing. This is an important formula. I don't know, by the way, if you want to use your calculator to calculate this. For example, you know that on the calculator you have a separate button for ln and a separate button for log. Yes? This you will find it on all calculators. But if you want to calculate log of 3 in base 2 using your calculator, then what you can do?
I think you take you divide.
Yes, that is the formula which is missing. I don't know, that's an important formula. So there is a rule that if you have a log a b, you can write it as log. It's very strange in the beginning, but it is true. You can switch to this formula. So if you want to calculate the log of a in the base b, you can calculate the log of a in the base 10 and then calculate the log of b in the base 10 and then divide them. So that is a little bit strange, but this is true. You can also do it like that. You can also calculate, so you can use this button to calculate this, or if you want, you can write ln of a divided by ln of b. So then you can use this button to calculate that. So in principle, if you have log of a in the base b, you can go to any base, like c. It doesn't matter. This is called the base change formula. Of course, you have to respect that a is positive, b is positive and not equal to 1, c is positive and not equal to 1. So let me write them. A is positive, b is positive and not equal to 1, c is positive and not equal to 1. Under all these conditions, you can use the base change formula for the logarithm. Yes?
It's meant to be divided by log of b, right?
Yes, thank you. Thank you very much. So here, I have chosen c to be 10. In this one, I have chosen c to be the Euler number. So whenever you want to calculate such a thing using the calculator, either you can use this button and this formula, or this button and that one. Okay? Of course, you can understand that is not very hard to understand why this formula is correct. Let us just understand that. See, if I call log of a in base b to be some number n, yes, then what is the meaning of this? This means that b to power m is equal to a. Yes? Let me call this number to be log of a in base c. Let me call it n. Then this means that c to power n is equal to a. And let me call this number p, for example. Then this means what? C to power p is equal to b. So I want to prove that this relation holds. I give these logarithmic numbers a little better name by calling them m, n, and p, and immediately I realize by definition of a logarithm I will have these conditions. Yes? Okay, so what can I do here? I can take this b away and put c to the p instead. So this gives me c to the p to the power of m is equal to a. Yes? And then this means that c to the power of pm is equal to a. But what is a? A is equal to c to power n. So instead of a, I write c to power n. Now compare these two results. C is positive and not equal to 1, and c to some power is equal to c to another power, and they are supposed to be equal. So what can I conclude? Yes?
That PM is equal to M.
Yes, that Pm is equal to n. Yes? So I showed that if I call this m, if I call this n, and if I call this p, by the definition of the logarithm, I realize that p, this number, multiplied by that number, is the number in the middle. Yes? So what does it mean? It means that m is equal to n over p. Yes? If I divide everything by p. But what is m? M is this number, n is this number, which is this number, and p is this number, which is this number. So we prove that this number is equal to this divided by that. So the proof is actually very, very simple. That is just the definition of the logarithm written in a little bit convoluted way, so that you might think this is strange, but this is very natural if you see that. Yes? So now that you know, or at least I reminded you about this formula, you probably will be able to answer that question, okay? Now my question for you is this. I want to answer the last question mark here. So what is that one? What happens if I have a logarithmic function but a base is not the natural logarithm? So for example, f of x equals to log of x in base, I don't know, have I written a? Yes, let us keep a. So this is, and by the way, we can move it up. Yes, good. So we want to answer what is the derivative of this one. I think you can answer it yourself now. So how should I do that? I want to find the derivative of this function. What is the first step to do? Which logarithmic function we know the derivative of? Natural logarithm. Yes? And we also learned that we can switch to log in base 10. We can also switch to natural logarithm. So that is probably the natural one to do here. Yes? So f of x can be written as ln of x over ln of a. And I want to differentiate this. I want to test your understanding, how alert you are, yes? Do I need the quotient rule here? It's a fraction. Do I need the quotient rule to differentiate it? If that is the answer is yes. We haven't studied that yet. But do you think I really need the derivative of a fraction because I am facing a fraction? Do you think I need that formula first to be able to calculate the derivative here? Yes?
No, you don't need it.
Why? What?
Because ln of a is 1 over a.
No, not 1 over a. It's 1 over?
1 over a.
No, don't make it complicated. Okay, anyone else? Yes?
Can't you see it as a multiplication?
Multiplication by a constant. Yes, that's exactly. So what I have to write, I have to deform it in my head as 1 over ln of a multiplied by ln of x. You told me 1 over a. 1 over ln a is just 1 over ln of a. I cannot do anything with that. Yes? Yes? And then this is a constant. Why? Because a is a constant. So you can call this c. F of x is c multiplied by a function. So its derivative is the same constant, which is 1 over ln of a, but multiplied by the derivative of this function. Derivative of this function we know. We just learned. It is what? So it is 1 over ln of a. The derivative of this is 1 over x. And then if I want to combine them, it becomes x ln of a. So that is the answer that I put here. So I will put it here. So the answer to this question mark is 1 over x ln of a. It's a little bit strange because you start with a logarithm in the base a, you end up with a logarithm in the base e. But that is what it is. So log of x in the base a, its derivative becomes 1 over x times ln of a. Yes? Understandable? Okay, but now there are some interesting things in this book. This is one of the reasons that I have chosen this one. I want to talk a little bit about those before finishing this topic. This is, for example, is not in the Origo book, but it is in the book, so I think it's good to know about them. First of all, a natural question is that what happens if I have two of them variables? For answering that, we have to wait for the quotient rule. Why is that? For example, if I ask you that what is the derivative of log of, for example, sine x in the base cosine x? If you want to answer the derivative of this one. Okay, if I want to use this rule, I can write it as ln of sine x, of course in its domain, yes? It's so wherever they are defined. I have to write it divided by ln of cosine x. But unfortunately, this is not like this because ln of cosine x is no longer a constant. So I need to know the quotient rule. So in the future, you can do that, but not right now. Okay? But now, I want to ask you this question. Instead of asking this question for logarithmic functions, let me ask the question for these type of functions. Here, I have chosen the base to be x, the exponent to be constant. Here, the base is constant, the exponent is x. What happens if I have x to power x? Yes? What happens if I have x to power x? So let us assume that x is positive, and I define you a function like this, x to power x. Now I ask you what is its derivative. So this is something that you need to learn, the method. But I want you to think a little bit about that yourself. X is a positive number, so by the way, even I don't know if you want to draw this, we can use GeoGebra to draw the graph of this function. We can see it later, okay? But right now, I want to ask what is the derivative of this function. Here, both the base and the exponent are simultaneously variables. So none of those methods will work. The polynomial function will not work because the exponent is not constant. Exponential function will not work because the base is not constant either. So what can I do? There is a nice trick to do this. It's very simple, and I think this is good to learn. Otherwise, you have to learn it at university. But this would be part of the lesson because it's in the book. So how should I do that? Any ideas? The first thing, instead of f of x, let us write y. Okay? The second thing, you need to know this trick. This becomes you take ln from both sides. You say that if this number is equal to that number, then ln of this number should also be equal to the ln of this number. Yes? But now, oh, you cannot do it right now. Yeah, sorry. Because so we have to learn it after the product rule. So because this will go to the back of the ln, this becomes this. Yes? And this is possible because I have assumed that x is positive, so I don't need to be worried about moving things back. But then this becomes x times ln of x, and then we know the derivative of x, we know the derivative of ln of x, and in the future we learn how to find the derivative of the product. So then we will be able to do that, but not right now. Okay? Okay, we cannot do it right now. So let us keep it for the future, but we will study that. Because if I know that, then it is easy. I take the derivative from this side, it becomes y prime over y, and then I know how to do this. In the future, we will learn how to do this. And then I want to find y prime. I multiply everything by y. But what is y? Y is this expression. So in principle, if I know how to calculate this, I am done with y prime. But this we will learn later. Yes?
Isn't x ln of x just x over x?
Pardon? Here?
Yes, should not be.
No. X should go to the back.
Yes, but x ln of x, ln of x, ln of x is 1 over x.
No. I don't know why you have this impression.
Because it's in the table.
No, I cannot. That's my question. This you cannot continue. If you want to take the derivative of this one, you cannot choose the second one differentiate. This is something we haven't studied. Pardon?
I'm just simplifying.
No, no. This is not simplification. I am not saying ln of x is equal to ln of x is 1 over x. I am saying if the function is f, its derivative is 1 over x. I hope that you are not confused all the way around, yes? ln of x is not equal to 1 over x.
Why is it in the formula?
No.
Oh, yeah, sorry.
The function, its derivative is this, not it is equal. So how is that possible? Sine is cosine, cosine is minus sine, yes? Its derivative is that. Yes, hopefully that you are not confused. Okay, so we still have some functions to put in this table. I think the only function left for you is tangent. So, of course, you will add some more functions here in the university, but that needs one more formula for us in this lesson. Yes, and we will talk about that later. Because for calculating tangent, I cannot do it unless I know the formula for a fraction. Tangent is sine and cosine. I know the derivative of sine. I know the derivative of cosine. I need to find a way to find the derivative of a quotient. If I can do that, if that's one part of the lesson, we will be able to finalize our table at the level of the high school for you with one more function, and that is tangent of x. Yes? But before leaving that, we can have a trick. I want you to learn this trick as well, okay? It's important. And by the way, we can do the tangent right now using this trick, if I am not confused, okay? The weather is so cold, my brain is not working properly today, I think. Yes. How much is that? It's minus 17 now. It's going down. Okay, so let me give you this. Even though you haven't studied the quotient rule, but you are, let me see. Yes, if you are smart enough, you can do it. You can do this one for me with a nice trick. This trick is called logarithmic differentiation. Yes? Can you find the derivative of this function? This would be one section in the book known as the quotient rule. Yes? But what I'm claiming right now is that if you can find a nice trick, you can do the derivative of this right now with what I have taught you today, even if you don't know the quotient rule. The trick is very similar to this trick. Think along these lines. And I want you to know this title. I don't know if this is in the book or not, but yeah, I don't see it in the book, but if you use it in the exam, that is acceptable for me, because sometimes it makes calculations extremely simple. Okay, can you tell me what can I do here? Okay, the first thing we do, we take absolute value, but absolute value of a fraction is absolute value of its numerator divided by absolute value of its denominator. The reason that I am taking absolute value because I want to take ln, and I want to make sure that when I'm taking ln, I will not have any problems with negative numbers. So then I take ln from this one. If this number is equal to that, then absolute value of this one is equal to absolute value of this fraction. But we have a formula. Absolute value of a fraction is equal to the absolute value of the numerator divided by absolute value of its denominator. And now if I take ln, I don't have any problems because these numbers are positive now. So then it becomes ln of absolute value of x plus 1, absolute value of x plus 2. Yes? But the interesting thing is, ln of a fraction, do you remember Mat 3c? It becomes ln of the numerator minus the ln of the denominator. So if I continue, it becomes ln of absolute value of y. The numerator becomes ln of absolute value of x plus 1 minus absolute value, ln of absolute value of x plus 2. Okay, now this function is equal to that function, so I take the derivative of this function. It should be equal to the derivative of this function. Yes? Now, do you see the board? Let me raise it. So what is the derivative of absolute value here? The derivative of absolute value, ln of absolute value of x, is 1 over x. It doesn't matter. But here it is not x, it is y. Can you tell me what should I write here? What can I write instead of this? So let me remind you here. If I give you ln of absolute value of x and differentiate it, we learn the answer is 1 over x. Now I want to do the same thing for y. It becomes the same rule, but y is not x. I have to multiply by y prime. That's the chain. But what happens on the right hand side? What is ln of this? The derivative of ln of absolute value. It becomes 1 over x plus 1, but multiplied by x plus 1 prime. And minus the derivative of this one, again, according to that rule, is 1 over x plus 2, but according to the chain rule, I have to multiply it by this prime. Okay, one more step. So let me write y prime over y equals to, the derivative of this is 1. 1 multiplied by that is the same thing. The derivative of this is 1 multiplied by that is the same thing. But I am looking for y prime. So I multiply everything by y. Yes? And that is my derivative. But instead of y, I replace this instead. So this becomes x plus 1, x plus 2 multiplied by this expression. So that is the derivative. So this trick is good, especially if you have a very complicated function, because in the future we will learn that the quotient rule is really a bad rule because it's complicated. So if you have f over g, if you want to differentiate this, you need to differentiate f once, multiply it by the same g. You need to take the derivative of that, multiply it by f, subtract them, and then divide by the denominator to power 2. So this formula is actually not a very efficient formula, even though that's correct. So if I make the fraction complicated, using this one is very hard, but using this trick becomes very simple, or simpler. Yes? Now we will talk about that. So in principle, this is your derivative and you are done, even if you don't know the quotient rule yet. So this method, that if I have a fraction I take absolute value first, and then take ln, and then take the derivative, and then multiply by the function, it gives you the derivative. This method is called logarithmic differentiation. Yes? Yes, I think we are now done here. So I covered whatever we need to. Any questions? I will talk about this a little bit later when I talked about the quotient rule, and then I want you to compare which method is more efficient to do the derivative of a fraction. Okay, for the time being, just take it as an example. If you don't understand what is going on, please let me know. Is every step clear? So I gave you a fraction. We take absolute value. This is necessary because I want to take ln. Something should guarantee that what is in front of ln is non-negative. So what I did, I just take absolute value and then take the ln, and then I use the formula for ln to break that fraction into a difference. And then term by term, I differentiate. The derivative of this one, if you want, I can write this one for you as well. ln of absolute value of u prime is 1 over u multiplied by u prime. Yes, that's always the case. So I use the chain rule here, here, and there, and then I want to find y prime, so I multiplied everything by y to get rid of this y. But this is common that if my function is in terms of x, the derivative should also be in terms of x. So I replace y again with my function, and I get this. So that is my derivative. Yes? So you see that the answer is a little bit complicated. And of course, if you want, you can simplify that a little bit by multiplying this in. This one and that one are gone, so it becomes this. And then when I multiply that, it becomes x plus 1 to the power of 2. And if you want, you can take the common denominator. This becomes x plus 2 minus x minus 1. So the answer is actually simple now. That is the simplified version. And if you use the quotient rule in this case, you will get the same answer. At the end, you will see that later. Okay, so I think that's a good point to stop. Do you have any questions? So what is left for us actually are two rules, and this chapter is finished because the differential equation is also omitted from this lesson. We will study extensively in Math 5. So that's a good choice, because if you want to study differential equations, it is better to study it in a good to a good extent. So they have moved it completely to Math 5. Yes, so the people who have only this lesson, they don't need to study it. So one more lesson. I can finish both of them in one lesson. Okay, but I will not put the exam for you before Christmas because you have one exam in Math 5, and then we can decide about the exam of this chapter after Christmas. Yes. So let me stop this video and then I will answer your questions. Thank you.